Okay, so here are some practice problems for projectile motion. You only need to be prepared for 3 styles of questions. 1, a graphical analysis that compares motion on the x and the y-axis. 2, an object that is launched horizontally off of a cliff. And 3, an object that is launched at an angle. So this first question here, old AP question, an object is launched at an angle, and we are asked a couple questions about it. Classic, we've got 1 graphic and 3 questions. The first question, how do the speeds compare? Well, we know that this is on the way up, and that's on the way down, and because of the projectile motion, or the symmetry of projectile motion, those velocities are the same. And because of the law of inertia, we know that if an object is moving without forces acting on it, it continues to move. And so the true velocities of these objects are the sum of their vectors. And so in this case, we have the lowest velocity at Q, and we have equal velocities at P and R. And so the correct answer here would be D. The next question, which one best shows the direction of acceleration? Well, acceleration is always working here. It's what causes this object to slow down. It's acting here in the downward direction, and it's acting here in the downward direction. An author is trying to catch you into thinking, oh, right here the y velocity is 0, and so there must be a 0 there. And that's true if you're looking at y velocities, but in this case acceleration always constant, always down. And this last question, which of the following best indicate the direction of the net force? Well, the net force is always in the direction of the acceleration. And if we've just identified an acceleration straight down, well, then the net force should be straight down as well. Correct answer, A. Okay, we've got another object launched at an angle here. This question wants us to break down what we know about acceleration and velocity. And if we consider an object that is launched, the velocity in the y direction will start large and positive because it's going up, and then eventually will end up at 0, and then it will move into large and negative and look like that. So there's a velocity graph. Now, acceleration, an object in the atmosphere flying along is always under the influence of gravity, pulling it down, and so there will be a downward acceleration that slows it down, stops it, and brings it down. That acceleration will always be negative. And so we're looking for a downhill and a negative here. Correct answer should be D. Okay, here's an IB question. We've got an object, in this case it's a football, and it is kicked at an angle with a given initial velocity of u, and we have an angle theta. And the question is, what is the expression for the range of the football, or how far it will go? Well, we know that moving in the x direction, this object will have constant velocity, and anything with constant velocity, you can use this equation for. And so here we just need a velocity times time expression. So the question is, what is the x velocity here? Well, this is the first step in any projectile motion problem, separating the true velocity into its x and y components. And here, with this triangle, we want an x piece of information that is adjacent to the angle. And so we need an adjacent trig identity. In this case, our adjacent and hypotenuse is or cosine, and so we need a cosine relationship here. And so you can probably go directly to the correct answer at this point, just to justify the math. Our velocity in the x is equal to u cosine theta, because the cosine of theta is equal to velocity in x over u. And solving for velocity in x, you get this expression. Correct answer, B. Let's not forget to multiply that by time. Okay, here's a pretty common question. We have a gun being fired horizontally. Bullet goes through the air. We know it has a continuous velocity in the x and an increasing velocity in the y in the downward direction. This question asks what might affect the time for it to hit the ground, and we can choose between mass or the launch velocity. Well, we all jump off the top of a cliff. We accelerate down at the same value, always negative 9.8, so mass is out of the question. It cancels. This question is asking, really, if you shoot something slow or you shoot something really, really fast, does that affect how long it takes to get to the ground? And we know from our conclusion of the bullet and the gun experiment that it doesn't matter how fast it's moving horizontally, so long as it has a velocity in the y direction that is 0, it will always take the same amount of time as a bullet that has just dropped down. So the correct answer here would be neither M nor V, D. Here is a similar problem. We have an object that is being, again, launched horizontally. And the question is, with the variables initial velocity and mass, which one of these will affect the distance traveled? Well, the faster you launch something or shoot something, the further it goes. So certainly, initial velocity, whether you're saying v or u, that initial velocity will increase the distance. But then, as long as the launch velocity is the same, a certain mass will not affect how far it goes. And so the correct answer here would be that only b, the initial velocity, will make a difference. All right, here we go. We've got a velocity that's launched with velocity v. And in this case, we're ignoring air resistance. So if you double the mass of this projectile and launch it with the same velocity, what following path will it take? Well, in the previous question we just looked at, mass doesn't really affect how you push through the atmosphere if you ignore air resistance. And so in this case, we're going to go with exactly the same line. I take D. Okay, an object moves in the XY plane. Graph below shows how the component Vx and Vy vary with time. And so no surprises there. We have a sideways velocity in the x direction that's constant. And in the y direction, we have an object that starts going up fast, comes to a stop, and going down fast. And this is clearly an object that is in a parabola. So in this one, a stone is thrown from a cliff, lands in the sea. We are ignoring air resistance. So which one of these four statements is correct? A, the vertical component of the stone's displacement is constant. That's not true at all. It starts at the cliff height and goes to max height and then falls to the ground. Vertical component changing all the time. Next choice B, the horizontal component of the stone's displacement is constant. That's not true at all. It is starting at position 0 and increasing in the positive x direction. C, the vertical component of the stone's velocity is constant. Well, that's not true. It starts going up fast, comes to a stop, and ends going down fast. D, the horizontal component is constant. That's absolutely true. We know when we break down velocity in the x and y, it is velocity in the x that is a constant value all the time. I would go with the correct answer, D here. Okay, throw a ball horizontally from the top of a cliff, ignore air resistance. What is the correct statement of the change to vertical and horizontal speed? Well, we know when something goes flying off a cliff that its horizontal speed is constant. It's been assessed over and over and over, and so we are looking at no change. We must take B or D here. Well, let's take a look at the vertical speed. We know that with vertical speed, it starts going up and then ends up going down. And so there's an absolute change. Even if it's horizontal, it starts at 0 and then increases in the negative y direction. So you would expect an increase in vertical speed because this is horizontal, I see. And then we would have the correct answer, no change and, increase and no change. Okay, we're on the moon for this one. Horizontally thrown, edge of a crater on the moon. That's their way of saying no atmosphere. What is the correct description of horizontal velocity and vertical velocity? Well, you throw something, projectile motion, the horizontal velocity stays the same. We keep seeing it. And so we've got to go stay constant A or C here. Well, the next option is vertical velocity. We know that horizontally projected, it will start moving in the downward direction. And so its vertical velocity is increasing at a constant rate. And so it stays constant, increases at a constant rate. Let's talk about A. This is a free response question that includes both graphical analysis and kinematics with some projectile motion thrown in. The premise is that we have a 50-kilogram cart and that it is moving on a track, eventually goes flying off it. We are given 3 questions here to analyze this graph with. Indicate the time for which the cart is at rest. Well, we'd be at rest on an xt graph here, and a lot of students will make that mistake. But because we are on a vt graph, we are at velocity 0 here on the 4th second and velocity 0 here on the 18th second. B, the time intervals for which the speed is increasing. Well, starts going fast and slows down to a stop. And then it speeds up in the negative direction. Now it's a little bit awkward because these are increasingly negative, and so some people might think that's smaller, but this is a velocity, and because velocities are vector quantities, the negative just represents backwards, and so sure, it's getting increasingly negative, but it's increasing in values. The magnitude of the speed is larger and larger, and so between the 4th and the 9th second it is increasing even though it's negative. And then it reaches a maximum velocity here of -1, slows back down, constant at -0.4, and then slows down to a stop here on the 18th. It then speeds up in the positive direction between the 18th and the 20th second, and so we have 2 time intervals for which the speed is increasing. And then we have to determine the horizontal position after 9 seconds, assuming the cart starts at x equals 2 meters. And so what we have here are 2 triangles. So we need to calculate the area of this triangle. That represents positive displacement. And then we'll have some negative displacement here. Now these triangles are almost the same size, except that this one covers 5 seconds, where this one covers 4 seconds. And this math here, 1/2 base times height, would give us 1/2 of 0.8 times 4, and that would be 3.2, half of that, 1.6. We've got a displacement of 1.6 here, and then a displacement in the negative direction here. This would be 5 times 1, 5, half of that, 2.5. And so we would have to take 1.6 minus 2.5, and we would end up with -0.9. But remember, it started at 2, and so if it started at 2 and goes -0.9, it would end up at -1.1, so the final answer, 1.1 for this. Next part of this question is to convert the velocity time graph into an acceleration time graph. You'll remember that the velocity time graph will give us acceleration in the slope. So for the first 4 seconds, we have a slope of down 0.8 over 4. 0.8 over 4 would be 0.2 negative, and so we need a 0.2 negative slope for the first 4 seconds. Now, once the object stops and starts going in the negative direction, we've still got the same slope here, and so we have the same acceleration that has slowed it down. It will now speed it up negative, and the slope of this line is going to be exactly the same up until the 9th second. So we'll continue this line out to the 9th second. Then this object is moving up from -1 to -0.4, so that is a slope of rise 6 and running 1, 2, 3 seconds. 0.6 over 3 would be positive 0.2, and that goes how many seconds? That goes until the 12th second. Lastly, 0 up until the 17th second, because it's stationary, and then we have a pretty rapid deceleration and acceleration here. And this slope, we've got a run of 3 and a rise of 0.4, 5, 6, 7, 8, 9, 10, 11, 12, 12 over 3, 4. 0.4 up until the duration of 20. And then lastly, we have constant velocity, so no acceleration. That slope is 0. So here is our acceleration time graph. So the last part of this problem is a simple horizontal motion problem. The cart just goes flying off, no angle. We're given a little bit of information here. We are given that the height of the table from which it leaves is 0.4 meters. And the question is the time it takes to hit the ground. Well, it's going to arc through the sky, but we know that the time to go flying through the sky is no different than just to fall straight down. So we need time down. We would know that the change of position is 0.4, that the acceleration is -9.8, and we would know that the initial velocity in the downward direction is 0, and we're looking for a time. Displacement, acceleration, velocity, and time is this relationship. And because the initial velocity is 0, we end up with this relationship, solving this expression for t, bring the 2 over, divide out the a, square root both sides. And so the time to fall 0.4 meters is equal to square root of 2 times 0.4, all divided by 9.8. I'm ignoring negatives here, but you'd have a negative on the top and a negative on the bottom that cancel out. Gives me an answer of 0.285. I'm going to round that up. 0.29 seconds. All right, the next part of this question asks, what is the horizontal distance from the end of the track to the point at which it lands? So in this case, our cart goes flying off, and we are curious to know its horizontal distance across the ground. We know that velocity in the x direction is a constant value, but that's not explicitly given here. You'd have to look back to the velocity time graph, and if you look at the velocity time graph, the velocity is equal to 0.8 meters per second. And so this distance is equal to velocity times time. We just calculated the time straight down. It was 0.29. And the velocity at 0.8 gives us a value of 0.232 or 0.23 across the ground. The last part of this question wants us to determine the kinetic energy of the object right as it's about to hit the ground, right before it hits the ground. And we haven't really looked at energy yet, but this points out a really important part of projectile motion, determining the final velocity of an object as it moves through 2 dimensions. If it's moving through 2 dimensions, you have a velocity in the y and a velocity in the x. And you have to take those 2 component vectors and put them together to be the true velocity vector. So let's take a look at what that looks like. We have in the x direction a constant velocity of 0.8, and in the y direction an increasing velocity. From this kinematics relationship with initial velocity being 0, we can simplify that expression to a final velocity equals root 2gh. This isn't given in any data booklets, but I recommend that my students memorize it. This comes up all the time. It can be derived from kinematics or the law of conservation of energy. It's a really important equation. Calculating our velocity in the y here, we've got the square root of 2, 9.8, and the height, if I remember right, I think it's 0.4 meters, table height. And we've got a negative and a negative that will cancel, and this value will give us a velocity of 2.32. It would be negative because it's in the downward direction, but that's going to cancel out here in the Pythagorean theorem in just a second. We basically have a right triangle here with 2 known values, 2.32 in the downward direction and 0.8 in the sideways direction in the x direction. And to Pythagorize this, our true velocity value will be equal to the square root of 2.32 squared plus 0.8 squared, and that gives us an answer of 2.9 and some change meters per second is our final velocity.